thanks everyone for joining us today. We are glad to have you for our first episode of the Graph Gurus webinar series, which is for developers. And today's presentation is called Building an Enterprise Knowledge Graph with RDF and a Graph Database. Before we start, I'm going to go through a couple of housekeeping items. And as I said, we're all the attendees are muted, but you can chat with us via the Zoom interface. And we will have the Q&A at the end, but you can go ahead and ask questions at any time using the Q&A feature within Zoom. And we are recording the webinar. We will send a link to the webinar later this afternoon, and it will have the links to everything to download the steps that we are going to be showing. And if you want to go ahead and download the developer edition, you can go ahead and do that right now. It's an instant download via email. So today, I'm going to go ahead and introduce our speakers. Victor Lee is our Director of Product Management, and as you can see, he has an extensive background in computer science and technology, and he has a PhD in graph data mining. So I'm going to go ahead and hand it over to Victor.
Thank you very much, Emily, for that introduction, and welcome to everyone who has joined us today. We're really excited to have you. And I'm excited to also be joined today with Xinyu Chang, my colleague and friend, who is our team leader for solutions engineering. And because we are going to be doing a lot of demo today, he is going to be walking us through the demo. He has a master's in computer science, is working on his PhD. He is a co-author of our GSQL language, so he knows it inside out. And importantly, he has actually helped deliver production solutions using TIGERGRAPH and GSQL for a lot of our major customers. So our agenda today is we're going to kind of let you know what is Graph Gurus. This is our first episode, so I want to kind of set the table. And then we'll go right into the topic for today, which, as Emily said, is building an enterprise knowledge graph from an RDF data set. And we will conclude by giving you a chance to ask, and we'll respond to your questions. So what is Graph Gurus? Our focus, we're a graph database company. We love what we do. We know that you are interested in graph, but not just from an academic standpoint, but you're probably working in some enterprise where they're considering or already using graph to solve some business problems. So we want to show you from our experience and knowledge where you can use a graph and what's the best way to use a graph to solve what type of problems. And so it's not just figuring out the right graph model. That's a question we're often asked. How should I model my data in order to best use a graph? And then you've got to get the data out. You have to get the information, the insight out. And so that's building the right queries. So overall, through this series, we want to help make you as knowledgeable, as smart about graph as we are. So the format is we're going to do these short webinars. We think they're going to be less than an hour long. They're going to be aimed at developers and data scientists, and they're going to be presented by developers. So they're technical, but not too technical. And for each one, as we show examples, we're going to have some code and some data, and those will be made available to you to download so you can replicate what you see. Sometimes you'll be able to follow along. Sometimes it'll probably be a little too much for you to literally follow along in your system, but since you can watch this later again in recording, you'll have the data and code, and then you can reproduce what we've done at your leisure. So episode 1, building an enterprise knowledge graph from RDF. And so I think many of you know what RDF is. It's a data format. We'll talk about that in a bit. So first of all, just to make sure we're all on the same starting point, what is a knowledge graph? it's a very commonly used term, and there's not really a strongly defined meaning for it. So it is a network of interconnected entities, usually focusing on one general area of knowledge, so one domain. But any graph is interconnected entities. So what makes it different from any other graph? It's usually the fact that the relationships have some more clearly defined semantic meaning. And also that it sort of implies that you can look at a chain or a set of these relationships and come to some conclusion. So, maybe logical inference from looking at a series of these semantic relationships. And so when you talk about an enterprise knowledge graph, you're just saying that the domain of knowledge is going to be an enterprise, centered around a particular business or a particular market segment. So why use TIGERGRAPH, which is a property graph, to build a knowledge graph out of RDF data? So first I should probably explain what's a property graph versus what. If you've looked into the graph database market, you may have seen that there are basically two flavors of product. There's property graphs and RDF graphs. And so RDF data is based on these triples of subject, predicate, object. Each one is basically making a statement of fact. And so an RDF graph is a collection of these facts. Whereas a property graph is more like, it's more related to a general purpose relational database, but expanded to the graph concept, where a node or a vertex can have properties, and an edge relationship can also have properties. So it's not strictly built up on these ideas of just triples. It's more like objects which have properties, and some of those objects are vertices, some of those objects are edges, but they all have properties, just like objects have properties. So why use data which is designed for one architecture, an RDF architecture, and use a TIGERGRAPH graph? Well, from a concept, RDF graphs are great. They were really developed from people who are thinking about the knowledge in an abstract sense. The databases were built to satisfy an abstract need. And so the problem is that they don't always give the performance that you need. They functionally do what they're supposed to do, but in the real world, they're sometimes not fast enough, or the query language doesn't satisfy all the real world needs that people have. So the takeaways from this episode is we're going to show you we're going to give you a general purpose schema for how to use a property graph to fulfill any RDF data set. We're also going to show you some examples of multi-hop queries using the GSQL language, which can give you that real-time response, as well as with our Graph Studio visualization system, you'll be able to see the results of those queries. So sometimes people talk about, they talk about building a knowledge graph. So you get the data in, but now what? Having a database is not really useful unless you can extract information out of it. So what type of queries do people typically ask with a knowledge graph? First of all, they often search. Are there any examples of this? You state some particular thing or some little pattern. You do some of that semantic reasoning that I mentioned. If this is true and that is true, then are there any instances of this conclusion? As you would do in any graph, you can analyze it holistically, searching for trends and norms. So in that case, you need to kind of take an aggregate view. And that's something that maybe the Sparkle language is not really geared for doing. Discovering outliers. That's kind of the flip side of trends. Once you understand what's normal, then you can see what's abnormal. and then just doing a more open-ended exploration, starting from some point, just kind of looking around you and seeing what do you see. Maybe you'll be surprised and you'll discover something new that way. So that's kind of the background of the problem of the case that we're looking at today. And I'm going to transition now into the demonstration. So Xinyu Chang is going to introduce our example data set. He's going to show how we can build up a generic knowledge graph schema, and then how we map our RDF data into our TIGERGRAPH graph database. And then he's going to show you examples of several queries so we can extract knowledge from that graph. So I am going to hand it over to Xinyu now.
Okay, hi everyone. This is Xinyu from TIGERGRAPH. So today I will show you how to work on an end-to-end solution based on this RDF data with TIGERGRAPH system. Okay, so I will. So during my presentation, I will show you how to create the universal graph schema to handle the RDF data, and also show you how to load the RDF data into the TIGERGRAPH system, and also how to do graph analytic based on the graph we constructed. Okay, so in the beginning, I want to show you the data set that we are working with. Okay, so we use this DBpedia RDF data set that is from 2016. This is actually a very popular RDF data. It has a vast community that work on this data set, and the total size of this data set is 150 gigabyte. And after the seminar, you can actually download it and play with it from this link. Okay, and so here I want to introduce a little bit on the format of RDF data. Okay, so RDF data contains 3 parts. Okay, so for each row of RDF data, they have, oh, I think we should move this a little bit. It has 3 parts. That is the subject and the predicate and the object. Okay, so it's always demonstrating a relationship like A likes B. Okay, so here in this simple example, that is A is the subject. Okay, likes is the predicate, and C is the object. And in this PDpedia data, you can see for this line, this article serves as the subject and is cited by another article, and another article serves as the object of the triplet. Okay, so the data here is called the N-triple format. We have a lot of different formats in the RDF data, and a user actually can select a certain tool and can easily convert one format to another. And here in this demo, we used this N-triple format of RDF data. Okay, and there are certain difficulties in working on RDF data if you use the traditional approach. As we all know that TIGERGRAPH actually is a property graph database. Usually we create a certain vertex and edge types for our solution, like in the picture on the right hand side. Okay, we have a lot of different type of vertices and edges in different color and icons. Okay, but it is very hard to define such schema for RDF data, because RDF data is schemaless, and it can have a limited number of vertex and edges. In this way, the schema can grow when the new data being ingested to the database. So here, we actually have defined a universal schema to handle the RDF data. Okay, so for RDF data, as I mentioned, right, we have subject, predicate, and objects. Okay, so we define the universal schema to handle all that cases. So here, the entity here, that it can be either a subject or an object. We put them under the same time same type because an article can serve as both object or subject, because it can be article A can be cited by B, and the article C also can article A can be cited by B, and it can also cite other articles, right? So in this way, article A serves as both subject and object. So here we use the same vertex type entity to represent all the entities in the RDF data, okay? And between the entities is connected by an edge called hasObject with a string having the value of predicate stored on the edge. And also we create vertices for this predicate values. This is created for a reason. I will explain it here. Okay, here is the example on how to load, example of loading one line of RDF data to the graph. Okay, so after loading this RDF line to the graph, the subgraph below will be constructed. Okay, you can see the blue color, which is the subject connected to the object with an edge, and also both of the subject and object are also connected to the predicate value. Okay, so the predicate is created as a vertex is for a reason, because each vertex will serve as an index node, so that we have this predicate vertex. So it serves as an index, will speed up your graph analytic. Okay, by giving a simple example, having this predicate as a vertex, so that you can start from the predicate and get all its neighbor subject, then we'll get all the subject that have this specific predicate. Like I can get all the entities has the predicate is cited by. All the articles has the predicate order, right? So it serves as an index. Or we can also start from the predicate to get all the objects that are associated with the predicate. That means whoever served as the co-author, all the articles that have ever been cited before, okay? Then we can actually start from a certain type. Like I can get all the entities that ever served as the country, then I actually get all the country this way.
So Xinyu, can I ask you a question here?
Yeah.
So it seems like what you're saying is, by building this structure, let me confirm my understanding, by building this 3 vertex and 3 edge structure from one data line, even though it seems like we're maybe blowing up the data size, it seems you said we're building an index. So we're actually building like search indexes along with the data. Is that correct?
Yes, the predicate will serve as index to get all the subjects having this and the objects having this predicate.
Right, and then so actually each of these 3, the subject is a hub for all its relationships, the object is a hub for all its relationships, and the predicate is a hub for all of it, that type of relationship. So each one is a search hub in itself.
Yes.
Great. Okay, thanks.
Okay, so after this structure is defined, we load the RDF data to TIGERGRAPH with this loading job. Okay, so here you can see all the edge types we have defined in the schema, right? Because in our schema, we have 3 types of edges. That is between entities, a subject has object, and also the other 2 is between subject and the predicate, and the object and the predicate, right? And you can see all the 3 edge types has been used in this loading job. That means for each row in your RDF data, we'll create 3 edges, okay? It's like create a triangle subgraph based on each line of your RDF data. And you can see this hasObject edge is created between subject and object. And we also store the value of predicate on the edge and in the string type. The reason we store the predicate is that during your traversal, we can select one edge type, okay? For example, given the city, I want to find everyone who born there, right? Then we can actually, starting from the city and the filter out those unwanted predicate values, only keep the born in, then I can get everyone that born in that city, okay? And also, we use subject and predicate as a from and to ID for sub has predicate edge, and the object and the predicate ID as the from and to type ID for the object has predicate edge. So this way, each row will create 3 edges. Okay. And after running this loading job, a graph actually can be created. And based on the graph created, we actually implemented 3 queries. Okay, I'll show you them with a live demo. Okay, so here is Graph Studio. It is the front end of TIGERGRAPH system.
Shinyu, this is Gaurav. There have a couple of questions from the audience. Can we address a couple of questions and then we can run into the demonstration?
Yeah. Okay.
So one of the questions was, are the object, subject, and predicate all functions in GSQL? That was one.
So I think the question was referring to the specific slide showing our loading code.
That's right.
This one.
And yes, those highlighted, the color highlighted subject, object, and predicate, those are functions. You know, Shin, you could say a little bit more about those.
The functions in the loading job, they are customized user functions for cleaning up the RDF data. Because inside the data, we have the, we use the function, we remove some brackets. And also
there's a note right there at the bottom.
Right. Our user-defined functions that parse the RDF syntax. That's true. Like for predicate, I will only keep the string in the end of the URL, right, to make the query cleaner, loading faster, right. And like for the subject, I would remove the brackets in the begin and the end. It's actually just parse functions to clean the data up. Okay. Is there any other questions?
Yeah, there was another question that was related to the schema, whether we need a schema in TIGERGRAPH, or are we making things limited by adding a schema to the TIGERGRAPH? The fact that we have a universal schema added, is that the best way to do it? Is there any other way? Are we limiting anything as a result of doing it? Can you address that a little bit? Are there any limitations because of this schema on the particular implementation?
Yes, to create a TIGERGRAPH solution, usually a schema is necessary because every data we load into the graph has to follow a certain defined graph schema. However, for this RDF case, with this universal schema, we don't touch it anymore. It is final, right? This universal schema actually can solve all the RDF problems. Yeah, so by using this schema, we have no limitation. But if you are working on a general TIGERGRAPH solution that you have a complex graph schema defined, this way, after your initial version of schema defined, you can dynamically update your graph schema at any time you want without putting your service offline. So our schema is actually pretty flexible, and I don't think that will give you any limitation.
Excellent. Thank you, Shinyu. Now we can switch over to the demonstration.
Okay, then let's begin to work on the demo. So this is a front-end UI Graph Studio of TIGERGRAPH system. So with the UI, we can actually implement end-to-end solution by just drag and drop. And here is where the graph schema is defined. And we can also check some statistical numbers of the loading job. you can see after running the loading job, we have 200 million of vertices and 3.2 billion of edges loaded to the system. Okay, so after the data loaded, we can do some graph exploration from this type. That now I randomly selected 5 vertices under each type, and I can just randomly expand one of those to show you. Okay, why don't I just print 5 entities? Okay, and these are the entities, and I can expand one of those by just double clicking it. Yeah, and then you can see all the predicate connects to it, and all the objects that belongs to it are expanded from it as its neighbors in the subgraph. Okay, and here I can show you the predicate stored on the edge. Okay, so here we can see that between this article and the date, there is a date as a predicate, right? Means the date of this article is 2007, January 13th. Okay, and the title of this article is KSFO radio hosts take on bloggers allegations, right? And also we can see all the predicates that is relevant to this article. And we can see the work of this article is the San Francisco Chronicle. And also we have an author for this article. And by double clicking on the author, we also can see everything that is relevant to this author. Okay? Okay, this is how we explore the graph. Other than yeah.
So Shinyu, did you, again, could you repeat for me the difference between the red neighbors and the green neighbors? And,
right.
And also for those, we might have some in our audience who don't see the colors so well. So
okay,
there are 2 different types there. You can see the different icons.
Right. By looking at the schema, we can see different vertex types are under different color and icon, right? So here we have the green vertex as entity. Entity means it can be either subject or object. And the red vertex is the predicate that is relevant to the subject or object. So in the exploration result, the green entity in the middle, Joe Garofalo, is the author of that article, right? So in this triplet, this article serves as a subject, and the author serves as object, and the predicate is author. Okay, so this way we can see that this object also has a predicate connected here as author, right? And also the subject article has an edge also connect to the author. It means that it ever served as subject in this triplet and had the predicate author. Is that clear enough?
Great, thank you.
Okay.
Yeah, let's move on.
Okay, so based on the loaded graph, we actually implemented 3 or 4 customized queries in GSQL. Okay, okay. Let's get started with a simple query. It's called get selected object. Right now we are looking at the GSQL query. It's actually the Turing complete full functional query language that you can implement any of your business logic with just a GSQL. Okay, so according to the definition of the query, here is the query's name, and these are the parameters of the query. And you can see we have 2 parameters. One is the input entity, and the other one is a string type predicate value that we used for the filtering. And the logic is very simple and straightforward. That is, starting from the input parameter vertex, and then I get all the has object edges, and then I filter them with a where clause. that I need the edges has the predicate value equals to your input predicate value. Okay, and after collected all those qualified edges, I want to store them into a list, and then I want to print it in the JSON result. Okay, so let's just try to run it. I got some, yeah. So I use this person as the input. So that means I want to retrieve all the type info of this person. Okay, okay, and here is the visualized result. Okay, then we can see this highlighted vertex is our input. It's a person. Okay, then we can see every type info regarding him, and we can see he's a generalist. He's let's see, he's a natural person, and he's also a writer. He's we know he's an agent, and he's also a thing. Actually, it's funny because everything in RDF is a thing. Okay. Okay. Yeah. Yeah. Do you have any question? Okay. So that's the simple query, and now let me show you some advanced use cases. Like for this get most related person. So this one is the query that getting an input person, I want to output the top K most related person via common objects. Actually, the traversal plan is like this. Starting from your input person, get all the common object as its neighbor, okay? And then find the person that shares the common object. And I keep the top K of the person who shares the most common objects. And also I want to know that this guy is actually a person because I only want person to be in my result. Okay, so let me run the query. Okay, let's keep the top one guy, the most related person in this case. Okay, change to code. And we can see this is our input, okay? And this is our result. And we know all the common objects shared in the circle are the stuff that they are in common. And we can see with this this guy as the input, we have we know that the result with the input that they both attend the Super Bowl, right? And they both play American football, and they serve in this team, and they also both of them born in 1984. Yeah, and this is everything that that are common between them are listed in the middle circle. Okay, and we can also try a larger number of K. Like say, okay, list the top K relevant person. Yeah, then it will return a larger result. Actually, you can see that even with 3.2 billion of edges loaded here, we can get results just in real time. Yeah, and let me move to the next query, which is the get top publisher. So for this query, we will have a place as input, and we want to output the top K most productive publishers who born in that place. Okay, so I will just take New York as the input, and you can see this query for traverse flow is just like starting from your input place, get everyone who born there, and collect the number of published articles for each person, and then sort of the persons born there according to the number of published articles. Okay, so taking top publishers, run it. Okay. Yeah, New York is huge, and you can see we have So this vertex is the New York, and we can see these are the authors that who born in New York, and these are the articles has been published by the person who born in New York. And you can see there is a Harvard node having huge amount of published articles here. And this guy is actually a quite famous guy that he actually published, let's see, like 984 articles that has been recorded by Wikipedia. Yeah, and we can
remember this data set, DBpedia. This is basically everything that could be extracted automatic or semi-supervised from Wikipedia. Is that right?
Yes, that is correct.
So everything that could be extracted from Wikipedia. This is all the New York authors and all their publications. Do we have some limit on does TIGERGRAPH or Graph Studio have a limit for what it could show or compute?
For query language, it has no limitation. It actually can compute anything you want. But for Graph Studio, it actually has an entity limitation that we can only visualize the graph entities up to 5,000. That means you can maximally have 5,000 edges in your visualized result. Yeah, and maybe we can try a easier example in this case. Let's use Pittsburgh as an input, okay? Then we can see that for Pittsburgh, we only have one author on the record, and this is his name, Donald World, and then he has only one public, that is the Catholic Standard. Pretty funny thing is that all these results actually can be accessed from the internet. This is his publication, and you can also find his wiki page from Wikipedia. So that is actually all the result here is actually you can find it from the internet. Yeah, and this is the second one. Okay, so for the third one, it's called get related topics. So its logic is given the input predicate. I want to get all the related entities, and then starting from those entities, I traverse k steps until I collect enough more information on what is the most related entities to your input predicate. Okay, so your predicate can be anything that ever served as a predicate value. For example, I can use, okay, let's return the top 30, okay? And let's use database as your input predicate. Okay, and change the layout to circle, sphere. Okay, and this is the most related articles regarding the the input predicate database, right? It's kind of like a word cloud, right? You output all the most relevant keyword regarding your topic. So we can see that we have the programming languages, the operating system that is the most related to the our input, the database as a predicate in database, right? Okay, Victor, do you think it's necessary that we also go over the details of the queries?
So we can check with our audience. So we have pretty much come to the end of our presentation, our planned presentation, but we are certainly able to, we have about 5 minutes left to answer your questions. So would you like us to, anybody out there like us to describe the query code, the GSQL code in more detail? If you have any questions, please submit them now. This is your best chance to get an answer. We will, of course, remember the recorded webinar will be available, so you can go over this in more detail. We're also going to be sending out the query and loading code for you to replicate this if you'd like. And then you may have more questions later, and we'd be happy to answer them.
Yeah, so, Victor, we already have a couple of questions. Let me ask them. First question is, how is this query language different from Neo4j Cypher?
Okay, I can handle that one. So both are graph query languages, of course. Cypher is based on pattern matching for the most part, whereas GSQL is more about graph traversal. That's a subtle difference, but in graph traversal, think about starting from a set of given vertices and then going step by step to neighbors according to some rules and constraints. And then at each step, you can perform some computations and aggregations if you so choose. Go on to another step, again, more computation. So the GSQL language is built on this graph traversal model. You can certainly build a pattern out of that. So it covers patterns, but it's more computationally complete. If you're familiar with the term Turing complete, GSQL is Turing complete. It's also a little bit better designed for parallel computation, so it achieves better speed. So those are some of the differences, but GSQL can basically handle what is done in Cypher. So it's possible to translate between the two, at least in the direction Cypher to GSQL. It's not always possible to translate in the other direction.
Excellent. Thank you, Victor. One more question. Where can we get more query examples, such as get related person? And then there was also a request from multiple attendees to describe the syntax of GSQL. If we can go over the GSQL query, for example, the get most related person query on another query, and just kind of walk through that, if you would, Victor or Shinyu.
I can let Shinyu do that. I'm going to suggest, did you go over get selected object already? Because that's the simplest one.
Yeah, this is the simplest one.
Did you do that already?
Yeah, I already did it.
Okay, yeah, try then. If we use up, we'll go a little bit. Emily, can we go overtime a little bit? Or do we have a strict cutoff?
No, go ahead.
All right.
If people have to jump off, they can.
Okay, then, so this is the get most related person query. So this part is our query parameters. So after this query is installed, you can actually send this parameter over via your RESTful request. They are just the request parameters. And here are the data structures that we defined for this query. These variables with single @, those are local variables. That means they are defined on each of your vertex. Okay, and in the beginning, we created two vertex, that is a person and a natural person. I just converted the ID string into the vertex type. Okay, then I start from the input. I start from the input and find all the object of your input person, right? And I pass along the predicate value to its description field, right? And then I want to make sure that the vertex visit won't be visited again, right? And then starting from the object belongs to your input, here I start from the start again, right? In the beginning, the start has a value of your input vertex. And after this selecting statement, the start is a vertex set, okay? Start actually becomes all the objects belongs to your input, okay? And again, I start from those objects and get the second hop neighbors from your input. And actually here, I collect all the edges to a list type of variable, okay? And after doing that, I starting from the second hop neighbors, and I only keep those that are connected to person or natural person to guarantee that all the second hop neighbors are person type. Okay, and after collecting all the persons, I sort them according to the set of the list, because in their list it has all the edges from your input to the second hop neighbors, right? That is actually all the passes. And since I sort the vertex set according to the list size of the list, then I know the most relevant person will stay in the will run will run to the top K of the query vertex list, right? So so that if I run it, you can see it from the result. Okay, and from the JSON result of this query, we can see all the evidence has been stored in the list. That is so showing how they are connected, and the query visualization will utilize this result to construct this this visualized subgraph, right? And that is basically what the query does. Okay.
Okay, Victor, is there any more questions?
We have several more that are coming in. I'm trying to see if there are any that we can answer quickly. You know, people asked, how is this similar to Gremlin? Basically, Gremlin is a declarative function-based language, and whereas GSQL is more similar to SQL. And I kind of said in general, Gremlin is more limited in what it can do than either GSQL or Cypher. Someone asked, can we export images in code and from Graph Studio to other platforms? I mean, certainly you can export data in a generic to a CSV format. You can export the configuration of your Graph Studio for later import into Graph Studio. So it's sort of a complicated question. What can you export? I mean, it's better answered offline. Is there a tool to transform relational database to TIGERGRAPH? So yes and no. The question is, how do you want to model it? If you want the data model to look exactly like your relational data model, you can do that. But that's not always that sort of sometimes it makes more sense to reconfigure the data. So if you want to do a simple direct transfer, it can be done. So I want to thank everyone for attending. We do have a couple more webinars planned already in the Graph Guru series. So next one is on building a recommendation engine. And then number 3 is going to deal with the topic of detecting fraud and money laundering. So you can see the schedule and sign up on our website. And lastly, just want to thank you and know that you can contact us and see what's going on in various ways. We're on Facebook, we're on YouTube. We've got this video will be on YouTube later. Those of you who registered, you'll get the link later today. But you can keep in touch with us in various ways, and of course, we would like your feedback. So please let us know what you think and what we could do better.